So we're now going to look at the third set of notes in this module, and we're going to begin analyzing the ideal gas on the canonical ensemble. Actually, in this video, I'm just going to get to the point where we are ready to calculate the partition function, but there are many things that we need to look at before that. So let's get started. So we'll do item 1 and we'll do part of item 2 in this video. The rest will actually be done in a later video. So this time we're just going to use the canonical ensemble. We won't use quantum mechanics. We will need to take account of some quantum effects, and this is what's called a semi-classical treatment. And semi-classical treatments are very common because we can't follow all of the particle trajectories, and so very often we are left to use a quasi-classical approach. This slide just reminds us what an ideal gas is. The interaction energy of the molecules is negligible, and so we can write the energy of the ideal gas in terms of the kinetic energies for each molecule. So the energies can be ordered, just like we did in the previous problem. We'll consider n particles contained in a volume V in contact with a heat bath at temperature T. We can specify the state of the gas simply by counting the number of molecules in each quantum state. And so Ni is going to be the occupancy of the ith level is the basic method that we'll use. We can calculate the energy just like we did in the simple example. And so this time we get an additional constraint, and the constraint is that the sum of the occupancies over all of the occupied states has to add up to the total number of particles. Sometimes we have to make use of that constraint, but actually probably not in this analysis. So what we would like to be able to do is calculate the partition function for a single molecule, and we've denoted that as Z1, and we would like to be able to use that to calculate the partition function for n molecules. The obvious way to do it, based on what we've done before, is to calculate the single particle partition function and raise it to the nth power. Unfortunately, the answer is wrong. So now we need to figure out why it's wrong, and we can illustrate that by considering two particles. So if we consider two particles, we could label the states as S and T, and then when we worked this out, that would give us a sum over the system where both particles are in the same state, and then we would have the sum where they're in different states. And then when we think about that, the problem is we can't distinguish between which particles are in the different states, because the particles are indistinguishable. So what that means is this particular calculation, when we just multiply, overcounts the number of states. And what that means is we have to figure out how to deal with that. We know how to deal with it because we've considered, for instance, four sums of golfers, and when we wanted to get rid of the useless rearrangements, that I called them, we divided by 4 factorial. Well, in this case, we've only got 2, so we divide by 2 factorial. But this gives us the correct expression for the partition function of a 2-particle ideal gas. So if we have more than 2 particles, what do? Well, we could generalize the sum. We would get a similar first term, and we would get a similar last term where they're all in different states. And in between, we would have some particles in the same state and some in different states. So how do we proceed? Well, it turns out that the probability of a single particle state being occupied by more than one particle when we're in the classical regime is vanishingly small. if a few of them have double or triple occupancy, they don't contribute much to the partition function, and we can basically omit them. So it turns out we can safely approximate the partition function by the last term in the expression of the previous slide. So that means that our n particle partition function looks like this. So our relationship between the n particle partition function and the single particle partition function is we do raise the single particle partition function to the nth power, but we divide by n factorial. And it's this process that makes it a semi-classical calculation, because a full quantum calculation would have shown us this result exactly. The n factorial is often ascribed to particles being non-localized, and what that means is if they are localized, in other words, for instance, if they were at specific sites on a crystal lattice, we could use that to distinguish the particle, and then we would not divide by the n factorial. Well, the next thing to do is evaluate this partition function, but that will be a story for another day. We'll wind this one up at this point.